So the next concept is particular forms of Maxwell equations. Okay. So particular forms of Maxwell's equations. Well, Maxwell's equations were given general Maxwell equations were given, and we know them, and they apply to all electromagnetic situations and for any type of time dependency. However, more often there is no need to use the general equation, or there is no need to resort to the general system. For example, we might need sometimes we may need to solve the equations at low frequencies. And in this case, uh, the displacement currents might be negligible, or the displacement currents might be negligible or doesn't exist. And in still other situations, the current densities or charge densities in the system, or both, may be negligible. Well, some of these representations are particularly useful, and therefore we discuss this here before we apply them to particular electromagnetic problems. Well, in particular, we will see the time harmonic representations of the equations of Maxwell's equations. Well, time harmonic representation. Okay. In time harmonic field, as you know, the dependency is sinusoidal. The dependency is often sinusoidal, and this is a form often dealt in engineering, and it is well known from circuit theory also. So there are two basic differences between time dependent and time harmonic forms. First, field variables as well as sources can be phasors. So field variables and sources, field variables and sources can be treated as phasors, and the second time derivative operator, which is d over dt, can be replaced by j omega, where j is a complex number which is equal to square root of -1. So now first, well, you from the previous course you already have an idea about phasors. However, let's revise first phasors. So you already know phasor notation is a method of representing of complex numbers. So if we consider a complex number b, which is equal to u0 plus j v0, where we have already said j is equal to square root of -1, which is complex. In this case, b can be represented in a plane called complex plane. So this is our complex plane. Here the u is real axis and v is imaginary axis. So this is our b, and projection of b to real axis is u0, and projection of b to imaginary axis is v0, and the angle between b and real axis is phi. And okay. And instead of writing b in this form, we can also write b in phasor notation, which is b multiplied by e j phi, which is equal to b by cosine phi plus j b sine phi. Okay, you already familiar with this notation? Here the b is, so b or this doesn't matter. B is the magnitude of our vector here, and phi is the angle between our vector and the real axis. And if we take b multiplied by cosine phi, we get we get u0, which is a real part of our number. And if we take b multiplied by sine phi, we get v0 from this drawing, which is a complex part or imaginary part of our number. And also the angle phi can be written as omega t plus theta, where the omega is the angular frequency, t is time, and theta is the initial phase angle. Okay, and if we take phi and replace it here, and here, what we get? What we get is b multiplied by e j phi is equal to b multiplied by e j omega t plus theta, which is equal in turn b multiplied by e j omega t multiplied by e j theta, and which is also equal to, so b by cosine omega t plus theta plus j sine omega t plus theta. Okay, now we, okay, here mistake, here should be also b, j b sine omega t plus theta. Now we have seen that how to represent complex number b in terms of, well, in terms of phasor, or in terms of the sum of cosine and sine. Now, what if we have a function in the form of, so we have a function, for example, f1 x y z and t depends on x, y, z and time, which is equal to, if this is equal to a0 depends on x, y and z, and multiplied by cosine omega t plus theta, or another function f2, again x, y, z and t, which is equal to a0 x, y and z multiplied by sine omega t plus theta. The phasor notation of these two functions will be, so phasor notation of the first function, so which is a0 x y z multiplied by cosine omega t plus theta will be the real part of our complex number, which is okay, there is lack of space. A0 by A0, which depends on x, y, and z, multiplied, we said e to the power of j omega t multiplied e to the power of j theta. And similarly, the phasor notation of second function, which is a0 x, y, and z multiplied by sine omega t plus theta is equal to the imaginary part of our phasor notation a0 x, y, and z multiplied by e to the power of j omega t multiplied e to the power of j theta. Okay, where the notations of this notation means the real part of our complex number, and this notation means the imaginary part of our complex number. So finally, we may define also phasor as the part of the function which does not contain time. For example, if we have a function ap which depends on x, y, and z, which is equal to a0 x, y, z multiplied e to the power of j theta. Okay, we have no time here. This can be also written as, so a p x, y, and z equal to a0 x, y, and z, and here we are showing the amplitude and the phase theta. So if we summarize the phasors can be written in three different forms. So let's take our function ap, which is x, y, and z. Phasors can be written in three different forms. First is a0 x, y, z e to the power of j theta is called exponential form. Exponential form. So Okay, and again the same function can be written as we have seen here, a0, x, y, and z, and we are showing the phase. This form is called polar form. And finally, phasor also can be written as in rectangular form, which is a0, so, sorry, a0, which depends on x, y, and z multiplied by cosine theta plus j a0 x, y, and z sine theta. And the third form is called rectangular form. Okay, let me write it here. So we have exponential form of phasors, polar form, and rectangular form of phasors. All three are the same, just these are the matter of notation. Okay. For um, for our purposes, we will use polar form of phasor, particularly for representation of results, because it is a more compact method of writing. So the rectangular form is also convenient in some cases because the rectangular form shows explicitly the complex variables of our function. So the reason for the use of phasors is so apparent. It allows the representation of fields in terms of magnitude, which is a0, for example, in this case, and a phase angle theta, without explicitly considering the time. Since the phasor in this case doesn't contain the term e j omega t. So when we need to convert phasors to time, the term e j omega t is simply added to our equation. Okay, now let's see one example on how to represent the functions, the phasors of functions. Okay. We are given a time-dependent electric field intensity as x multiplied by 10p plus j 20p multiplied by cosine 10 to 6 t minus 120y. We need to write this electric field intensity in the form of phasors. We need to write in a rectangular notation, polar representation, and exponential representation. Well, how do we start? First of all, we can see that electric field intensity is a complex number with okay, real part. The coefficient of real part is 10p and the coefficient of imaginary part of 20p. First of all, let's write it in the form of so in the form of which is convenient for us, we can write x 10p multiplied by cosine multiplied by cosine 10 to minus 10 to 6 t minus 120y plus j 20p cosine, okay, 10 to 6 t minus 120y multiplied by x. Okay, and now we may write this will be equal to x, okay, 10p cosine 10 to the 6 t minus 120y plus okay, plus j 20p sine 10 to the 6 minus, okay, 120 y plus pi over 2. Okay, here I add plus pi over 2. That's why cosine changed to sine. And each term can be written in rectangular form. Well, and from the if we compare with our previous equations here, I forgot t. If we compare to our previous equations, we may see that omega t in our case is 10 to the 6 t, and theta is minus 120y. Okay, one is theta 1, and theta 2 is minus 120y plus p over 2. Okay, and if we remove the term omega t from our phasor, it will have the form. So electric field equals to x okay x multiplied by 10 pi cosine minus 120y plus j okay j 10p sine of minus 120y plus 20p cosine of minus 120y plus p over 2 plus j 20p sine of minus 120y. Okay, no, plus p over 2. And we know that we know that cosine minus alpha is equal to cosine alpha, and sine minus alpha is equal to minus sine alpha. And if we apply it here, what we get? We get that electric field intensity E is equal to x 10p cosine 120y minus J 10p sinus sine 120y plus so plus 20p okay 20p of sine 120 minus plus J 20p cosine of 120y. And finally, we get x multiplied by so we have 10 10p cosine 120 minus j 10p sine 120. Okay, we get cosine 120. Yes, 10p. Finally, we get 10p plus j 20p cosine 120y plus plus or minus so minus j yes minus j 10p minus okay j 20p sine 120p sine Okay, finally we have this answer. Good. You may you may try by yourself the find the representation in polar form and find the representation in exponential form. Okay, now this is we have derived the rectangular representation of electric field intensity. Okay, this is all for today. Try to derive another two forms of this electric field intensity, and from the I think from the next lesson, from the coming lesson, we need to start electromagnetic waves.